Welcome back. Topic 3, Part 2. Derivation of fin heat rate equation. C. Example 2-5. Derive fin heat rate equation at constant cross-section area. Our goal here is to solve the fin differential equation to obtain temperature profile and then get fin heat rate equation. First, if the fin cross-section area is constant, the governing equation is represented in equation 5.1. Next, we introduce two variables. The first variable is theta, which is temperature difference between fin surface and fluid. Since T infinity is a constant, the first derivative and the second derivative for theta and T are the same. The second variable introduced is M, which is a combination of fin system variables, heat transfer coefficient, parameter, conductivity, and cross-section area. It is in the unit of 1/meter. Next, we plug in equation 5.1a and 5.1b to equation 5.1 to yield equation 5.2. This standard ODE has a standard general solution in the form of equation 6, where B1 and B2 are constants, sin h and cosine h are hyperbolic functions. Third, there are two thermal boundary conditions required to solve second-order ODE. The first thermal boundary condition is at x equals 0, the fin base, which is a constant surface temperature. The second thermal boundary condition is at x equals L, the fin tip, which is convection. By applying first law to the control surface at the tip, convection in equals convection out. Next, replace T dt dx with d theta dx and the temperature difference with theta to yield the convection thermal boundary condition at tip. Next, use the two thermal boundary conditions to obtain a constant B1 and B2. At x equals 0, plug in equation 6 to the first thermal boundary condition to yield equation 6.1 and then solve for B2. Remember, sin h0 is 0, cosine h0 is 1. At x equals L, plug in equation 6 to the second thermal boundary condition to yield equation 6.2, and then solve for B1. Fourth, plug in constant B1 and B2 back to equation 6 with some further mathematical manipulation to obtain temperature distribution, which is represented in equation 8. This diagram represents temperature profile over the fin length. Five, once we have temperature profile, we're able to find fin heat rate equation Q sub F. First, we apply Fourier's law to equation 8 at the fin base. Equation 9.1 defines the heat rate, fin heat rate, which is product cross-section area and heat flux. Next, plug in equation 8 to the theta dx to yield its derivative. Then take k and theta and m out of a bracket, plus negative becomes positive to yield the new form of equation 9.1. Second, we introduce a new variable, capital M, in the unit of watt. Equation 9.2 defines capital M, which is the product of conductivity, cross-section area, temperature difference, and M. Replace M with combined fin system variable. And next, take K AC into the square root to yield the new form of equation 9.2. Third, plug in equation 9.2 of M, new form, to equation 9.1, new form, to yield the fin heat rate equation with tip convection boundary condition. It is represented in equation 9.3. D. Summary of temperature distribution and fin heat rate for the uniform cross-section fin. You have seen this table before. After defining theta L, temperature difference, theta B, parameter, cross-section area, M, and a capital M, under different tip thermal boundary conditions, A, convection, B, adiabatic, C, given temperature, D, infinite long fin, we have different temperature distribution along the fin lengths and the fin heat rate equation. Here, this is the hyperbolic functions, and this is derivatives. E. Derive fin heat rate equation at non-constant cross-section area. If the fin has non-constant cross-section area, equation 1 is the governing equation. We take annular fin as an example. It has radius R1 at the base and radius R2 at the tip. The base has constant temperature Tb. The tip has adiabatic condition. The thickness of the fin is T. The distance between the two fins is S. It is subject to convection. The system is best described by the cylindrical coordinates. Next, we replace x with r, define parameter 2 pi r, and cross-section area. Then plug them into equation 1. As a result, dx becomes dr, AC becomes 2 pi RT, P becomes 2 pi R. This number 2 represents convection on both top and bottom surfaces. Second, we introduce two variables, the temperature difference theta and combined variable m. Next, plug in equation 2.1 for theta and m to equation 2 to yield new differential equation 3. By comparison with equation 3.1, this is a modified Bessel differential equation of order 0. It has general solution form in equation 4, where C1 and C2 are constants, I0 and K0 are modified Bessel's function of the first and second kind of order 0 respectively. Fifth, there are two thermal boundary conditions. One is at x equals R1, the fin base, which is constant surface temperature. The second is at R equals R2, the fin tip, which is adiabatic. Plug equation 4 into first boundary condition and the second boundary condition. Solve for C1 and C2, where I1 and K1 are modified Bessel function of the first and second kind of order 1. F is defined right here. Finally, we plug constant C1 and C2 back to equation 4 and apply Fourier law to get fin heat rate equation, which is represented in equation 6. By checking, apparently it is very complicated. As engineers, we need to find efficient way to calculate fin heat rate K sub F value. F. Engineering method to find fin heat rate Q sub F. First, fin efficiency diagram like this are made available for all kinds of fins. For example, in figure 3.18, The horizontal axis represents a combined fin system variables, characteristic lengths, heat transfer coefficient, thermal conductivity, and profile area. The calculation equation are presented in the diagram. The vertical axis is fin efficiency, the different solid line for different fins. If you can find the combined variables value, then go straight up to interact with the fin of interest, then go left to rate the fin efficiency. Second, from the efficiency rated, you can calculate the fin heat rate directly from equation 1. This method is much simple and effective. At this point, we covered topic 3. You expect to know and to learn how to use semi-differential control volume to derive fin differential equations. And second, based upon the fin geometries, whether it is constant cross-section area or not, you're expected to derive fin heat rate equation after obtain the temperature profile. See you next time.